many thanks for giving me also the chance to speak here today. Great pleasure to be here. So, I would like to tell you about a story relating to two topics, one from algebra and the other from geometry. On the algebra side, I will tell you a little bit about dt invariance, and on the geometry side, I will talk about counting curves, namely rational curves and toric and cluster varieties, giving so-called log chromometer invariance. And the main theme of the talk is to explain how dt invariance can be related to log chromometer invariance. And this is based on a couple of works we did in the last couple of years, and earlier similar relationships were known in particular cases in dimension 2. They were known as Kronecker correspondence for very particular types of quibbos called Kronecker quibbos. So these relationships we prove in these works with joint with period or joint with period provides generalizations of these to higher dimensions. So I will very briefly tell you about quibbos and how dt invariants are defined. So a quibbo is a finite-oriented graph with a set of vertices that we denote by Q0, set of arrows which we denote by Q1, source mapping an arrow to its source, and a target mapping an arrow to its target. So you can have something like this in mind as a quibbo. And when you have a quibbo, you can talk about a representation of a quibbo, which is an assignment of a vector space for every vertex. For instance, if you had a simple quibbo here with 3 vertices and 2 arrows, you can assign these vector spaces C squared C. And then you also need to assign a linear map between these vector spaces for each arrow. And the dimension of a quibbo representation is just the dimensions of the vector spaces you assign to the vertices. So here, the dimension will be 1, 2, 1. And to define dt invariance, we will look at a moduli space of all quibbo representations, but there's a natural notion of isomorphisms between 2 quibbo representations. We will look at pure representations up to isomorphisms. So you can imagine if you have 2 quibbo representations, you can ask to have isomorphisms between them and natural commuting diagrams. So we will look at the moduli space of all quibbo representations up to isomorphism, and in addition, we will look at semi-stable ones. So we have the notion of stability due to kink, which says that if you look at a quibbo representation of a given dimension gamma, and if you define your n to be the lattice Z to Q0, where Q0 is the number of vertices. Oh, I'm sorry about that. Thank you. So here, is the lattice Z to Q0, where Q0 is the number of vertices of your quibbo. And if you denote M as the dual lattice and MR the associated real vector space, then for any point theta in gamma perp, which is an element of MR, we leave it as a stability parameter, and you call your representation theta stable if for any sub-representation, if the natural pairing between theta and the dimension of the sub-representation is smaller than 0, and semi-stable if it's smaller than or equal to 0. So this provides a natural restriction on the moduli space. which I denote by m gamma theta. So you fix the dimension, you fix the stability parameter theta, and this is the moduli space of all semi-stable quiver representations of dimension gamma up to isomorphism. And then quiver dt invariants are roughly defined as the Euler characteristic of this moduli space. Though there are some subtleties here. I was looking at just a cyclic quiver in this example. Generally, if you have cycles, one needs to be a little bit careful. Whenever you have a cycle and you have cycles, you can additionally to the data of Q talk about the data of a potential, which is a formal linear combination of oriented cycles C. Given as this, and then there's a natural trace function you can define. For any cycle C, you can define this trace function just by taking the composition of the functions attached to these arrows in your cycle. And then you can define a trace function for your potential by taking the linear sum of all these trace functions. And then if you look at the critical locus of this trace function in your moduli space, in nice cases, like when your moduli space is smooth and so on, you can define your quiver dt invariance as the Euler characteristic of this critical locus of your trace function. And generally, most cases are not going to be nice, and there's a huge theory explaining how to define quiver dt invariance when your moduli space is not nice, which says roughly you need to replace this locally constant sheaf by some intersection cohomology sheaf, which is some perverse sheaf, and apply some vanishing cycle factor and so on. So there are a lot of technicalities here when things are not nice that I'm skipping. Okay. And one nice property to remember about quiver dt invariance is the admitted wall crossing formula. And before that, let me point out that we will often work with a rational version of quiver dt invariance, which we call rational dt invariance, which we denote by omega bar gamma theta, which for any dimension vector gamma and stability parameter theta are the associated quiver dt invariants up to some factor. So if you know all quiver dt invariants, this amounts to knowing all rational ones and vice versa, but working with these for computational purposes is more convenient because these are the ones that appear when you do wall crossing. So the nice property to remember about quiver dt invariance is that there's a wall in chamber structure in your space MR, which was due to this, and which amounts to saying that if you look at gamma perp, there's a chamber structure so that if you take any stability parameter within a chamber, your quiver invariant within this chamber, your quiver dt invariance will remain invariant, but if you cross to some other chamber, they will change, and they will change with a prescribed recipe given by so-called wall crossing formula. There is a particularly nice set of quiver dt invariants called attractor dt invariants, which are relatively easier to calculate. They are defined as follows. So you have your lattice N, and there's a natural skew-symmetric form on N, defined omega, defined on basis elements by aij minus abi, where aij is the number of arrows from the ith vertex to the jth vertex, and similarly aji. So if you use the skew-symmetric form, and for the dimension vector gamma, if you take the contraction of the skew-symmetric form along gamma, you will obtain a point in gamma perp, which we call the attractor point. And we will take this very particular point as a stability parameter theta. So the attracted ET invariants of a quiver for a given dimension vector gamma, which we denote by theta gamma star, are the DT invariants which are defined for the particular stability parameter theta, defined in terms of the skew-symmetric form by taking the contraction along gamma. And one can show that if this point lies by chance on some red wall here, you can apply a small perturbation, and it will be well defined. It's up to small perturbations. Okay, so attracted ET invariants are relatively easy to calculate. It was shown by Bridgeland first for acyclic quivers, and more generally by Langmuir for quivers which admit a so-called reddening sequence, which is a particular mutation sequence, that all the attracted ET invariants should be 0 if your dimension vector is not one of the basis vectors EI for n, and they should be 1 for everything else, for all EIs. And generally, we say these quivers have trivial attracted ET invariants. The definition of a quiver with potential to have trivial attracted ET invariants is that you want all your quivered ET invariants to be 1 for all I, for all your bases, if gamma is one of the basis vectors. And you want them to be 0 if gamma is not a basis vector. And you want this condition to be satisfied only for those gammas which are not in the kernel of your skew-symmetric form omega. And in this case, there's a conjecture of Bouchard, Manchot-Piolin, and Moscovo-Piolin, which says that if you have a quiver with potential, and if you describing the bounded derived category of coherent sheaves of X for a Calabi-Yau threefold or local Del-Pizzo surface, then QW, this quiver with potential, has trivial attracted ET invariants. So in some cases, there's a recipe starting with a quiver with potential to cook up the category of representations and match it with dBco. And the conjecture is that if you look at local Del-Pizzos, then these quivers should have trivial attracted ET invariants. And Bousseau, Descamps, Leflory, and Piolin proved this conjecture, for instance, for KP2. So in many cases, these, yeah.
Sorry, just to be sure that about the definition. So attracted DT invariant just means DT invariant of a specific special type of point.
That's correct, yes. Attracted DT invariants just mean DT invariants for a fixed dimension vector gamma and stability parameter theta, where you take your theta to be this very particular point defined by contracting your omega along gamma. Okay, and in earlier work of Koncevich-Seubelmann, back in 2014, they proved that if you apply iteratively the Koncevich-Seubelmann wall-crossing formula for these rational DT invariants, which fit well in wall-crossing setting, you can show that any rational DT invariant for any stability parameter theta can be expressed in terms of attracted ET invariants, where there's, as usual, some automorphism of permutations. So if the sum is over all possible decompositions of your dimension vector gamma into simpler vectors. So for instance, if gamma is 1, 1, this could be 1, 0 plus 0, 1. So you sum over all possible decompositions. And there's coefficients appearing denoted by FR theta and these are sums. These can be combinatorially calculated. These coefficients are given as sums from contributions of some trees called attractor trees. And I will tell you what these trees are in the next slide. So there is a way to express any dt invariant in terms of attractor dt invariance, and the difficult thing is to tell what the coefficients are generally. So these coefficients, if r theta t, are given by sums over some coefficients associated to attractor trees. So an attractor tree for a fixed parameter theta and direction vector gamma is a tree which is a rooted tree starting at theta, and in any gamma perp you go in the direction of the vector you define by gamma. Sorry, by this notation I just mean omega contracted along gamma, as before. So you flow in the direction of the attractor point, and if you decompose gamma as gamma 1 plus gamma 2, for instance, and the naive gamma I perps, you flow in the direction of the attractor points in those gamma i's, and so on. So this way you can define trees, and generally, while there is this universal formula of Kontsevich-Soibelman, the subtlety was to concretely calculate these due to the fact that these trees can be arbitrarily complicated. For instance, as here, they can be 4-valent, and the combinatorics usually gets complicated. But although they can be higher valent, they have the nice property to satisfy some tropical balancing condition, namely the weighted directions around every edge sums up to 0. So you can view them as kind of tropical trees. And what we did is to prove a conjecture of Alexandre Pioline, which just says that you can actually write a sum of any dt invariant in terms of attractor dt invariance, where you can define your coefficients not over arbitrary attractor trees, but over nice trees which are just trivalent. So the conjecture says that if you fix your dimension vector and stability parameter, any quiver dt invariant can be expressed as a linear sum over all the compositions of your dimension vector gamma of attractor dt invariants for gamma I, where the coefficients can be described in terms of binary trees. So the difference here is binary trees. And binary trees are those which are trivalent and such that they have as many leaves if you decompose your gamma into gamma 1 to gamma r as r. And to each leaf, you can think of associating the gamma i's. So this was conjectured by Alexandre Pioline a while ago, and we proved this together with Pierrick, and around the same time there also came up another nice proof of Moscovy, and it would be an interesting question we don't have a good understanding how to relate these two different proofs. This is very much on the algebra side. This uses operands that I'm not expertised with, but our proof is more like geometric and combinatorial. So I will tell you what the coefficients are. So the coefficients we concretely describe by, if you assume that your gamma is decomposed into dimension vectors gamma 1 plus gamma r, and if you, for this talk, if you do a simplifying assumption, if all these gammas form a basis for n, then you can describe the coefficients concretely as a sum of all these binary trees where there are some signs, epsilon, and you use the skew symmetric form omega, where here the sum is over rooted binary trees with R leaves decorated by gamma 1 to gamma R, as in the previous slide here, like here. And for any vertex, for any interior vertex in such a tree, here, gamma v prime and gamma v prime prime, for any vertex v prime or v prime prime, generally for any vertex v, are just the sum of the vectors gamma I, which are descendants from v. So if you have a vertex v here, your gamma v would be gamma 1 plus gamma 2, and so on. And so you just use your skew-symmetric form to define these coefficients, the subtleties to define these signs, where much of the work goes into. And to define these signs, you can take a small generic perturbation up to a small generic perturbation. These signs are defined as either negative 1, 1, or 1. And I will not talk about this technical point on how to define the signs, but it can be visualized to determine the signs as a tropical realizability problem. So, and it gets, when your dimension vectors don't form a basis, it gets a bit more subtle. Then you need to work at a bigger space, which we introduce to get well-defined signs here. So the technical point is the signs. And what we showed later on is a correspondence between these coefficients that are arising in the attractive flow tree formula and rational curves in a toric variety associated to your quiver. And I will tell you what this toric variety is and what kind of rational curves we are calculating. Okay, so I'm more of a geometry person, where we are finally coming to. I like curves much more than sheaves or quivers, contrary to Pyrrhic, who likes all. But if you do have any questions up to now, if anything was unclear, do let me know. Yeah.
How many of these attractor points are there usually?
So if you fix any dimension vector gamma, then this attractor point is uniquely determined by the point in MR. For any fixed gamma, there is one attractor point.
Just one?
Yes.
Yeah.
And
The attractor point depends on gamma.
Right.
So it's not
for any gamma, there's
a full spectrum. It's like on each gamma, there's a particular point in the space. For 6 particular gamma.
right, and the attractor flow tree formula, where because there are infinitely many gammas. Are there really infinitely many? You take decompositions, there are finitely many decompositions. Yeah. Yeah, for any gamma, there is attractor point. Here, the attractor flow tree formula thinks that if you want to look at quiver DT invariance of a given dimension vector gamma, you decompose it. You consider all possible decompositions. And then you can express it as attractor DT invariance for all these gamma i's which appear in that decomposition. It's a little bit similar to things we use like on the Gromov-Witten side when you look at a tropical curve representing a curve of a given degree. Sometimes we look at all possible decompositions of that curve with all possible contact orders summing up to that degree. If you are on the Gromov-Witten side, for instance, read gross ponder, ponder z-but, and so on. There's the analog idea there. Okay, so if you look at the quiver and potential, there's a natural toric variety, x sigma, you can define out of it. So you define it this way for any quiver and a dimension vector gamma. If you take any decomposition gamma into R vectors, then you can define a fan sigma in MR for a smooth projective toric variety, which is a fan containing all the rays you obtain by contracting omega along gamma I. So if you take the simplest quiver, Kronecker quiver just with 2 vertices, then you can see if you decompose, if you take the dimension vector gamma to be equal to 1, 1, and decompose it as 1, 0 plus 0, 1, then you can calculate the contraction of your skew symmetric form along 1, 0 and 0, 1 will give you these 2 rays. And then we just want to work with a projective toric variety to do some Gromov-Witten theory, low Gromov-Witten theory. So here, if you just take these 2 rays, you will just get a affine plane. So we will just complete it by adding rays to a projective one. And it doesn't matter at the end of the day which rays you're adding to complete. So if you add this ray, you will get P2 completing A2. You can add these 2 rays getting P1 cross P1. And it won't matter which completion you take because of the nice property of log Gromov-Witten invariance I will define, which satisfies some birational invariance. So if you take different completions, here you will get birationally equivalent things, which will have the same properties. Okay, so starting from a quiver with potential, you can describe a projective toric variety. Furthermore, you can describe hypersurfaces defined by the equation hypersurfaces inside the boundary, not inside your toric variety. So you can look at the equation gamma I, the primitive vector associated to gamma I. So gamma I doesn't necessarily need to be primitive. You take the smallest primitive vector in its direction. And if you look at the equation gamma I equals any constant and you restrict it in the toric boundary, you will get hypersurfaces in your toric boundary. So I'm going to define Kerr counts with given tangencies, Kerr counts in your toric variety with given tangencies with respect to these hypersurfaces. So I will define a moduli space which I denote by M gamma 1 to gamma R associated to your toric variety, which is a moduli space of genus 0 stable maps to your toric variety. I will take R plus 1 pointed stable maps, and I want to impose on the first R points the condition that they should map to HI on the toric boundary. So here I will take 3 pointed maps where my first point and second point should map to H1 and H2, and the contact order of the image of these points with the boundary should be equal to the divisibility of this vector you obtain by contracting gamma I along omega. And furthermore, I want to impose the condition that the image should intersect the boundary only at these points. Then in general, if you calculate the virtual dimension, so in this example, if you look at P2, if you look at a rational curve in P2 passing through 2 points, there is only one such curve. And so in general, if you look in dimension 2, you will get just finitely many curves. The virtual dimension in dimension 2 is 0. And the subtlety is to describe these invariants in higher dimensions. Because if you calculate the virtual dimension of this moduli space, it will be the dimension of your toric variety minus 2. So in higher dimensions, you will not get virtual dimension 0. And here, I just wanted to summarize the technicality that goes into the framework of log Gromov-Witten theory, which is a theory that allows you to define invariants out of higher dimensional moduli spaces like here. So if you have, for instance, a 3-dimensional toric variety, you will have a 1-dimensional moduli virtual dimension 1. And then we can still define invariants by essentially counting 0-dimensional strata in your moduli space. And to do it using the language of log geometry, I will just briefly tell what goes into this. Before that, may I ask at what time did I start? Half past, okay, I still have, okay, thank you. Okay, so the first observation is that if you look at this moduli space, I will not concretely describe what the stratification is, but I claim that there is a natural stratification on this moduli space of maps that defined this way, that we defined this way, and the existence of such a stratification is due to the fact that on your curves, you can keep track of different combinatorics of your curves, the contact orders of your curves, how they interact with the toric boundary. So this combinatorics on interacting with the toric boundary induces a natural stratification on your moduli space. In particular, there is a normal crossing divisor D in your moduli space. And using this divisor D, you can cook up a cone complex given as the dual intersection complex of D in your toric variety, which I denote by sigma xd. So this is a cone complex, so if you just have, for instance, P2 with the toric boundary divisor D given by the union of 3 lines, then the cone complex of D in your toric variety is a cone complex which is built from cones where you replace every codimension K strata of D in your toric variety with a K-dimensional cone. So this is a codimension 2 strata. You would, for this point, you would put a 2-dimensional, real 2-dimensional cone. Similarly for this and this. So if you have a toric variety, then with the toric boundary divisor, this will be the toric fan. Generally, and for your moduli space or for any space where you have a divisor, you can talk about this cone complex, which we call the tropicalization. And then you can look at the 0-dimensional strata of your moduli space, which we're interested in counting. And the 0-dimensional strata, due to constructions and tropical geometry and the reversal of dimensions passing to the tropicalization, corresponds to, one can check it, corresponds to n-2-dimensional strata in this cone complex. And it gives n-2-dimensional families of tropical curves. And our goal is to calculate the 0-dimensional strata in your moduli space. So to do it, we will calculate n-2-dimensional families. We will look at n-2-dimensional families of tropical trees and curves which tropicalize into families. So the idea to count curves which tropicalize into families of tropical curves is to view them as the generating limit of families of curves. Like the idea is to count as bad as possible curves in your toric variety, like which fall into the toric boundary, which arise as limits as families of curves, which will have the correct tropicalization. So,
question, sorry, sorry, if I took this data and did like the HTTP construction, would those be the wall-crossing functions supported on the walls given by the n-2-dimensional families of tropical trees? Is that a correct intuition or not?
Right, in the HGTV setup, they're very, very closely related. So in the HGTV setup, we would look at not a toric variety, but a blow-up of a toric variety. Yeah. And the wall-crossing functions I will talk about will come also as curves, which tropicalize to n-2-dimensional families. But these curves that appear here will sort of the ones that are related to HDTV curves, A1 curves by some degeneration. So, and in the HDTV setup, we always look at blow-ups of toric varieties along the toric boundary, and like here, if you blow up here, which amounts to using some degeneration argument to relate A1 curves to curves which have like a relative tangency along the toric boundary in the toric strata, plus some multiple cover contributions. So this modular space that I'm talking about is the part in HGTV where we have the toric variety.
Thank you.
Sure. Thank you for the question. Do you have any other questions? Okay. So So to be able to do log-Rama-Witten theory to count a zero-dimensional strata, which gives us, in our log moduli space, which gives us log-Rama-Witten invariance, we will build up n-2 dimensional families of tropical curves. I say here d-2, where d is just the cardinality of my set of vertices, alternatively the dimension of the toric variety x sigma. Okay, so how can we construct d-2 dimensional tropical curves naturally if we do quiver dt theory? So I mentioned there are these flow trees arising in your space of stability conditions for your quiver. And you can deform these trees if you vary your theta inside your gamma perp. What you get will be exactly d-2 dimensional families of tropical curves. And so we obtain such families of tropical curves of the correct dimension by deforming the attracted trees. So from the data of theta and the dimension vector, we get tropical types. And then we can look at the Gromov-Witten invariance of the tropical type, rho tau determined by theta and the gamma. So we first show that if you fix general hypersurfaces in the boundary of your toric variety, so these are the HIs that I mentioned given by the equations C2 gamma I equals constant. So if you choose your constants general in a general way, then we proved that if you look at maps, genus 0 maps, which match these hypersurfaces as we described, so the ith marked point goes into HI with the correct contact order, then the moduli space of such maps whose tropicalization is a fixed type tau, a rho t, determined by the data of the stability parameter and the dimension vector, then we have this Gromov-Witten invariance of which counts zero-dimensional strata of this moduli space, and we prove that there are finitely many such numbers for any fixed rho tau. And we showed that your coefficients expressing the contribution to fixed tree T is given, so the coefficients appearing in the attractive flow tree formula, we proved is equal to this number log Gromov-Witten invariant we calculate in the toric setup. Do you have any questions up to here?
I don't know, is there some intuition I should have about why that's correct?
So
Sorry, so it's a vague question.
it's a good question. So
What was it? Yeah. So this is. So it's like those attracted trees really are. I can think of them as tropicalization of some curves inside X sigma. Is that an accurate intuition?
that's true. Yes. So for any stability parameter theta and dimension vector gamma, you can get an attractor tree. Actually, you get finitely many attractor trees because fixing the dimension vector actually just fixes the directions of the unbounded edges of your tree. But the finiteness result is related to the fact that there are finitely many tropical curves of a given type.
It's kind of really cool.
And
That is not right.
yeah, so I don't have, thank you, very good geometric intuition. The proof at the end is motivated by the fact that there's wall crossing to calculate dt invariance, there's wall crossing to calculate log Gromov-Witten invariance. HDTV, and the walls appearing have exactly the same combinatorics. That's the main observation.
Thank you.
Sure. So I will tell you a summary of the proof in the toric case, how it goes. Okay, I told how we matched these two. In the toric setup, actually, I mean, we were motivated by wall crossing. In the cluster setup, the proof is purely combinatorial. But in the toric setup, we actually do observe this correspondence by a mysterious connection between calculating low-chroma-Witten invariance via the generation and gluing formula. And we just observed a mysterious connection where matching the coefficients appearing in the gluing formula, calculating this side, and the numbers I described here using the skew-symmetric form. So I told you these numbers. The coefficients appearing in the attractive flow tree formula can be expressed as a sum of numbers which are defined in terms of the skew-symmetric form. And we just matched these numbers with some numbers appearing in the gluing formula and punctured low-chroma-Witten theory. So here is a summary of the proof. We use the generation. We degenerate our toric variety into further toric varieties. And to define such a degeneration, we just use the data of the hypersurfaces and contact data. And so by a degeneration formula, we can express the low-chroma-Witten invariance as a sum over invariance in the central fiber of a toric degeneration of our toric variety. And there is a gluing formula due to Abramovich-Gross-Siebert telling you how these numbers of curves in the low curves in the central fiber are given by some number which can be defined by which we do relate to numbers appearing in the wall crossing for quiver DT invariance defined by the skew-symmetric form omega. And the main idea is to observe the skew-symmetric form omega appearing in the attractive flow tree formula is related to gluing formula and punctured low-chroma-Witten theory. So this was just a brief sketch of the proof, and a final question is, okay, I've so far talked about toric varieties in the toric setup. Can we find a correspondence between quiver DT invariance and log curves and cluster varieties? And so far I talked only about a correspondence between low-chroma-Witten invariance and coefficients appearing in the attractive flow tree formula. And there is a more general story relating directly low-chroma-Witten invariance of cluster varieties to not only the coefficients in the flow tree formula, but directly to quiver DT invariance. So if you start with a quiver, with a potential, as we mentioned, you can define a toric variety together with hypersurfaces in the toric boundary. If you blow up these hypersurfaces in the toric boundary, you get a cluster variety. If you denote the total space of the blow-up by X and the strict transform of your toric boundary by D, the complement of D and X by U is a cluster variety which admits a Poisson structure. And in this cluster variety, you can look at particular types of Kerr counts, which we call A1 curves. These are rational curves in this cluster variety meeting D at a single point with given order of tangency. And as you mentioned, these are exactly the curves appearing in the HDTV setup and which degenerate into curves in a toric variety that we mentioned in some multiple covers. And it's also the case that such curves come in D-2 dimensional families. Again, using techniques of low-chroma-Witten theory, we know how to extract numbers out of such counts by counting zero-dimensional strata. And here's the main theorem in the setup. So if you assume that your QW has trivial attractor, your quiver with potential has trivial attractor DT invariance, if you fix your dimension vector and your stability parameter, and if you look at the Quiver-DT invariant for this dimension vector and stability parameter, we show that you can express it as a sum of a low-chromavitin invariance of a given curve class beta, which we determine out of the data of gamma and theta. Here the sum is of a, so we're summing of a, so we're looking at the sum of all low-chromavitin invariants, which are of a given tropical type, which is again determined over omega and gamma, and there are finitely many such numbers which tropicalize to that type. So this is the final correspondence we prove, and the idea of the proof just amounts to observing, to calculate Quiver-DT invariance using wall crossing. One can look at the stability scattering diagram of Bridgeland, and to calculate low-chromavitin invariance using wall crossing combinatorially, one can look at the canonical scattering diagram and the scattering diagram combinatorially we defined with Mark Cross in our paper, and just match these diagrams from which one can deduce this relationship. And that's all that I wanted to tell you about today. Thank you for your attention.
Questions?
Yeah.
So maybe another kind of, so I should think about QW corresponding to some, so being the quiver such that it's like bounded derived category, which means like bounded derived category of some, maybe Calabi-Yau free form, is that right? And then, so I guess my question is, this is like a Calabi-Yau free category, like the, yeah?
Yes, it's a Calabi-Yau free category.
And then, so
right.
I should think about this, maybe this corresponds to some actual Calabi-Yau free form, and then we're kind of like looking at, I don't know, the stability manifold and
exactly. Yeah, that's a good question. I mean, in some cases, there exists an honest Calabi-Yau threefold and geometric DT invariants which do match the Quiver DT invariants. Like in some cases, for KP2, for instance, the local P2, you can cook up a quiver like. Pierrick will talk about this particular quiver during his discussion sessions. He will focus on KP2. So if you take quiver with 3 arrows everywhere, for instance, and a particular potential function, one can show that the category of representations for this Q and potential will match the bounded derived category of KP2. And then this will give directly a correspondence between geometric DT invariants and low-chromavitin invariants, which is a variant of MNOP, but you don't like to call it a variant of MNOP, which is different than MNOP. But yeah, it will give a correspondence between geometric DT and low-chromavitin, which is different than MNOP.
Thank you.
Thank you.
Yeah, maybe a bit of a random question. So
sure.
Usually people talk about attractor points on like complex moduli of complex CY3s. Here you're like in the A model moduli space, so is there some relation?
I don't really know.
So yeah, so when people do that, it should be related to stability conditions of the Fukaya categories.
Right.
Yeah. So here, like to match with this topic, and maybe you're in a situation where the Fukaya category might have a description of square potential.
Yeah.
And then this geometric attractability invariance, maybe its first approximation they should be related to this. So this is attractor points in the space of the equation of quiver. It's like a quiver version of the geometric attractor points. Right, yeah, so the analogy is a category of quiver representations here in the Fukaya category.
Yeah.
attractor points in complex attractor?
Yeah, so I'm much more a Kerr person, so I think of the fact that we can represent any quiver DT invariant to simpler attractor DT invariants related to this attractor points is an analog in my mind what happens on the Kerr side for A1 curves that we match. So in our previous work with Mark Ross, we were showing that if you look at A1 curves, which are curves in a blow-up of a toric variety along toric boundary that have only one contact data with the boundary, we proved the main work in the higher dimensional tropical vertex papers to prove any count of A1 curves can be calculated by starting just counting simpler invariants, which are given by very simple A1 curves corresponding to the exceptional curves. So we run an algorithm just with the data of exceptional curves we blow up. It's an inductive algorithm using tropical geometry. And using the data of exceptional curves, we can show you can find an algorithm to calculate all A1 curves in the tropical vertex. So in my mind, these attractor DT invariants are analogs of such simple curves from which you can cook up all other invariants.
If you consider compact radial, which is where people usually look at the attractor, then the corresponding attractor you find. So if you are able to define a count of special Lagrangians and look at this count at this specific point, I guess the expectation that for compact radial there will be typically non-trivial. There will be typically very interesting numbers which will match some Lagrangian entropy. And so here's a kind of pure attractor condition. This is some kind of condition which is a kind of non-compactness assumption. It's supposed to be true like for reasonably flat or non-compact radial. For cardios, for compact radial, there will be analogous story, but these numbers will be interesting. Like the number has the attractor points.
And one needs to really think carefully to define what does it mean for QW to have trivial attractor DT invariants. So we defined this in our paper for all dimension vectors which are not in the kernel of Gibbs symmetric form. So not for all possible dimension vectors, but we are just looking at very specific class of dimension vectors and want them to satisfy this. If we don't put the appropriate assumptions in this definition, this won't be true for many things, even for P2 or local P2 that Pirik will talk about.
Maybe I have a super silly question. Is there an example where the DT invariants of the quiver can't give open Gromov-Witten invariants? I mean, or maybe the question is nonsense, but I'm just curious.
Open Gromov-Witten invariants with respect to which Lagrangian?
Maybe some toric-radial prequel with some Lagrangian, and then somehow the counts of open Gromov-Witten invariants with boundary that Lagrangian agrees with some DT invariants of some quiver. I mean, it may not make sense at all, the question, sorry.
No, that's a good question. At the end, by fixing the stability parameter theta, you sort of fix a point in your, tropically, you fix a point where your tropical curve ends at. So I think heuristically, they should give some open Gromov-Witten invariants with boundaries on the Lagrangian over that point. But I don't know proof of this fact relating to those. But I think that's a heuristic expectation.
Thank you.
Thank you.
No further questions. Let's thank your speaker again.
Thanks.